Electronics for college. Today we talk about digital circuit again. Digital circuit. In the previous video, we introduced how to make a logic gate using transistor. Using various transistors, TTL, the Schottky, low power Schottky, and CMOS, NMOS. There are various transistor can be used for creating a logic gate. Now, we also talk about the advantage and disadvantage. The CMOS, most advantage is low power. Okay, and nowadays the size can be small by the progress of process technology. So this is suitable for making LSI. LSI chip is like a CPU, floating point processor, AI processor, or data processor. Data processor is like the web server CPU. Okay, so these are the competing at the smaller size transistor. Right now they're talking about 3 nanometers. Nobody's used 3 nanometer yet. Apple tried to use 3 nanometers, but actually 4 nanometer is what they get right now. So that's a CMOS, and we have a TTL and low power Schottky, make it faster and lower power. And this is actually not used for the large chip design this day at all. So this is one category of the technology. Okay, now beside that we have a technology called ECL, or sometimes CML, and this is used for high speed. Like a communication. Device, and not like a CMOS. Speed can be adjusted for each gate by allocating more current, more power to the gate. So gate speed somewhat customizable. Now you pump in more power, then the gate gets faster, so you can handle really fast speed like gigahertz. Like gate speed is like a picosecond level. But these days, because of the process technology advancement, just like a CMOS, transistor size gets small, so you don't have to pump in that much current to get the really high speed. Problem with the ECL is ECL historically used a negative voltage, and the logic swing, the voltage swing is smaller, so more strict the voltage high-low specifications and temperature control is harder to use. Okay, and in order to interface with this technology, you need the translator. Okay, but those are low power Schottky. If it's MSI medium size IC chip, actually use only TTL for interface, input and output, and internally it's a ECL. Okay, so that's a kind of trend. It's faster and better control. But because output voltage high-low is between 0 and 5, it's translated into TTL interface, input-output. So that's a kind of chip design usually used. But when it comes to LSI, the power consumption, total power consumption, become the issue. And that's why lowest power consumption CMOS is used for CPU, those large LSI chip. Now, high speed is a different story, okay? And also, this ECL is a bipolar technology, okay? And bipolar is also used in analog circuit. The reason is bipolar is more flexible, designing various kind of analog circuit. For example, AD converter, op amp, the voltage regulator, all kind of analog circuit. It's all bipolar. So it's the same category. Okay, the why bipolar is used. I think historically all the engineers spend a lot of time. The analog circuit is the hardest one for engineers. It's at least 3 to 5 years experience, because each circuit has very unique transistor level design and need a lot of experience. Analog circuit designer is not easy to be, because LSI chip, actually you don't work on transistor level. You have a logic element all defined in the library. So design effort will be strictly logic design. And also architecture. Architecture, you need to have many years experience. You need to understand the various architecture, the architecture's characteristic and good point and bad point. You need to have it. And also there are a lot of theory about how to reduce overall power and reduce the speed, like pipeline method or scalar method and stuff. Architecture need a lot of experience to do that, and the remaining is a logical design, how to design the logic unit. But ECL, high speed, bipolar high speed, and bipolar analog circuit is going to be totally different. Today we talk about this ECL circuit, and next time we talk about analog. This is a big subject. So besides this, there is another category in the IC chip design is power transistor. And it's not like LSI chip. The transistor itself is an issue. The MOSFET was used, field effect. The reason is bipolar was initially used for power transistor, but bipolar is current driven, and MOSFET is, as you know, the gate draw no current, and when you handle like a 20 amp high power, you don't want to drive this 1 amp gate. The gate current is almost zero current. You can still turn on and off. But these days, silicon carbide. The silicon carbide is not really silicon. it's not made by the diffusion. It's from crystal level. When you make a silicon crystal, the silicon crystal you melt from pot, you pull out, right? So like a 8-inch wafers. The silicon carbide you have to pull out from silicon carbide melting pot. So this is a kind of different technologies. There are only few companies they master this technology and dominating. What's so good about silicon carbide? Silicon carbide has a very large band gap. So remember the band gap, the energy level up and down. Between there's an electron and a hole moving around. This band gap is large. So what's good about it? Okay, breakdown voltage. So breakdown voltage is become larger. Okay, so nowadays those high power 20 amp and sometimes need 90 volt high voltage, the breakdown voltage. This silicon carbide is the best option. Now the new one coming out is gallium nitride. And the gallium nitride does the performance is as good as a silicon carbide, but this also the process technology is still new. These are the very hot area right now. You know why? Because EV, electronic vehicle, need those devices. Okay. Now MOSFET is the cheapest one, but MOSFET has a little bit problem on rise time. When you switch off, rise time is slow, and the power consumption, the efficiency of power consumption is not that great. That's why silicon carbide is preferred. It's more expensive chip, but it's silicon carbide is used the most of the EV, and the new one they try to use gallium nitride. So this is a different field. Okay, so we talk about that maybe later, but today we talk about ECL, high speed, how you make a high speed logic gate using ECL circuit technology. And next video we introduce some analog circuit. And as I said, analog, there are so many analog device to learn how to design, so it's impossible to cover everything by a few videos. So we pick a few of them, very basic one. So analog circuit is as I said, require quite a lot of experience to do analog circuit design. For example, the small signal amplifier used for audio device, and this require the linearity, very good linearity. How do you get the linearity? That's one of analog design requirement. The AD to increase the precision of the analog signal detection, and also very low voltage detection. How do you detect such a voltage? This is used for the battery management system. Like battery, you have to know how much current going through to the battery, and in order to do that, you have a 0.1 ohm, very low resistor. You don't want to put too much resistor; it's a voltage drop, and the energy consumed by this resistor. This is the current sensing resistor, very small. So the voltage between them is quite small, but when battery charged up, the current decrease. When current decrease, voltage get even smaller, and some point you have to know, okay, charging is done. How do you detect this such a voltage, like probably 10 millivolt or below, right? So each analog circuit has the challenge to design circuit at the transistor level, and you put that together into a silicon chip, then you have one chip AD converter, or one chip the op amplifiers, or voltage regulator, those stuff. So analog circuit is different animals. We cover only some basic stuff here in the next video. So let's get into high-speed logic gate, ECL. ECL is emitter coupled logic. So construction of this logic gate is quite different from single transistor TTL type of gate. Actually its emitter is coupled. And what do you mean coupled? This is a ground, and we go negative, and you have voltage swing resistor and transistor here and transistors here. These two transistors emitters coupled, and you have a constant current flowing to negative 5 volt. And actually this doesn't have to be this way. It can be plus 5 volt, and this can be ground for the circuit like a BIMOS. And what's BIMOS? BIMOS is a single chip, has logic like almost LSI, but this side is bipolar. And typically it's high-speed communication logic, whatever. Now on the single chip, this will be like plus 5 to ground, and digital is plus 5 to ground. But you cannot connect this on the chip because the transistor, the logic circuit side, this switch, many switch on and off, and it's quite noisy. This has a lot of noise, and if you connect together on the chip, this side is affected. So we have to keep these power line in the BIMOS separate, logic side and high-speed logic side. Or if analog, you may have to separate this too, because analog, this you don't want to have noise coming in. So digital CMOS is noisy, means plus 5 and the 0 has a lot of noise. Okay, and this side high speed hate the noise, so you isolate. And what do you do is outside the chip, through the coupling capacitor, to filter out the noise, you connect outside the chip. And this capacitor, there are multiple chip pins for the plus 5 and the ground. So each pin have this low pass filter capacitor attached to it, so the noise doesn't get on this side. Okay. Now you have a resistor here, and this is basically the gate of ECL. And now if you think about it, what is the voltage swing here? The voltage swing, this is input. This is called reference volt. Okay, so the swing is about 600 millivolt. And 600 millivolt, you want to have comfortable collector voltage for transistor. So say this is 600. So this voltage, the we think about output. Output is going to be like this. The reason why you take output from emitter is, number one, match up the signal level. Number two, the emitter output is a very high impedance, low impedance. The provide a lot of fan out. Fan out means it can drive many input, and that fan out can be is adjusted by this current. This is the gate current, and this is the output current. Okay, so if voltage swing about 600 millivolt, and this typically says 600, so when this is low, it's going to be negative 1.2 volt. Okay, and when this is high, means no current flowing. Logic is here, the voltage here, and this output, you take this output, this is going to be 600 millivolt drop. So the high is negative 600 millivolt. So this is roughly the voltage level. And when you design this kind of chip, you can determine by yourself, because you are not using external ECL spec. So external signal, if you bring this ECL signal, you have to follow the external ECL spec, and they have two different kind. There's a 10K spec and 100K spec. But when you use ECL circuit internally on the chip, then this can be up to you, your design parameter. This is going to be your design parameter. So what you do is you set this threshold voltage reference between this. So it's like 0.9, negative 0.9 volt. Okay? So what's happened is, if this voltage is, say, 300 millivolt above 0.9, like negative 0.6 volt, then this transistor, you compare with this is a comparator, right? You compare against this voltage. This is higher, 300 millivolt higher. So all the current flow this side, and this current is shut off. So the current becomes zero. This become high, 0 here, and 600 millivolt below. So this side become high, negative 0.6. And when current flow this side, you have a 600 millivolt drop plus 600 millivolts, so 1.2, negative 1.2. This become low. So when input is high, this guy input is high, then you have inverted output and also non-inverting non-inverted output. So logic-wise, this gate is going to be like this, and this is the input and output straight through, and another output. You have two output which is inverted. Okay, so if you make or put the transistor in parallel, just like CMOS design, and emitter couple here, and this is V reference, and you have a constant current going to the ground. Now you have A and B. Either one of them is high current flow this side, and this side is shut off. So this is a logic OR and NOR. You have a this is logic OR. Either one is high, A, B, then output becomes high. Where does this come from? Do you have a NOR? What you do is collector dot. We call that collector dot. So what you do is connect like that, then this becomes NOR output. Okay, now when you have enough voltage, like a 5 volt between, you can have a cascaded transistor. Just like a CMOS, right? The A, B, and you have a cascaded V reference and another emitter couple here, and this tied to the collector dot here. Okay, so you need a V reference 1 and 2, second level. Okay, so what second level? Second level is the A swing is going to be this reference is minus 9.9 volt, and this is one level low, so minus 1.5 volt. So this input voltage has to be minus 1.2 volt to minus 1.8 volt. So voltage level different. This guy A is minus 0.6 to minus 1.2. Okay, so this current flow only if this side, it's flow this side only if both A and B are high. So this is AND gate, and also you have a opposite NAND. Okay, so ECL, you always get the both output polarity. So now if you have a basic gate, you can construct any gate, any speed. So you can make a high-speed counter or high-speed decoder, whatever you need, using those gates. Okay, so far so good. So I can tell you may be wondering how we make this kind of constant current circuit. Okay, that's a subject for analog circuit. We will talk about it next video. Okay, so this constant current, the analog circuit, you have to know the technique of making constant current, constant voltage, current mirror, and the shunt current. If certain condition happen, then shut down everything, and also start up. This is when you have a positive feedback, and sometimes you apply the power voltage. You don't know which state it may latch up, so you need to have the Grace startup circuit. There are all kind of circuit technique you have to know, and that's analog, and some of them cannot cover everything, but some of them we will cover there. Okay, so now we introduce a second level signal. Using that, we can make a latch circuit. Basically, latch circuit is you have gate and you have a feedback. Okay, so this point feedback to other side, this point feedback to other side. Okay, so it's a positive feedback, and this is emitter coupled at the second level I, and this is the latch signal, and V reference to second level, and RS or D latch, whichever, say R S input. So of course this RS signal has to be settled before latch enable. Let's see, let's make it D, right? And this side is D bar. So when you have a latch, you have latch signal, you latch in the data. Let's see, is this correct? This sorry, this coupling is wrong. This has to be coupled, and this has to be coupled with this guy. Okay, so when latch is high, then D bar determine the state. Excuse me. When latch is low, then this emitter couple decide the state. It's preserve the state. Okay, so it's memorize the logic state. So when L signal high to low, here the data is retained, and when it goes high, data is acquired. Okay, so this is the latch signal. You put the two latch signal, the latch unit together, you can make a flip-flop. I hope you know that it's a logical design issue. We will cover logic design also in this electronics for college later, but yeah, two latch together, you can make a one flip-flop. So edge triggered flip-flop. Okay, so this is a circuit, and again, this constant current circuit is the subject of analog design. Okay, so we talk about that in the next video. So the logic switching gate, the switching speed is pretty much controlled by this current, how much power you push in, because the current is going to speed up charging, discharging parasitic capacitors around the transistors. So when current large, then this resistor becomes small, because if current is 10 milliamp and a 600 millivolt swing, so how much do you need? 60 ohm, right? It's a very small resistor. This is a pretty big current for current standard thing. The transistor size used to be big, as a 10 milliamp was common, but nowadays you see even microamp. It still perform pretty fast speed. Okay, so that's all for today's. We will see hand-on electronics next. If you like this video, please subscribe. Okay, I made a little sketch before assembling the circuit. This is the reference voltage generator, and the reference voltage 1.3 volt for the current sink, and this is emitter coupling. Each registers pick the closest value you have in the inventory, and this input is driven by this guy. This is emitter, output is going to be the input signal, and the voltage is divided here by this 5 volt pulse. So this guy move up and down about 600 millivolts, the higher or lower, and we monitor output, see what kind of characteristic we get. Okay, and now transistor we need is 1, 2, 3, 4, 5 transistor, so we have enough. This is the NPN, general purpose transistor, whatever I have in the inventory. Okay, finally ECL circuit is working here. There were many incidents. First of all, power supply died. $10 is a cheap one, so I end up with buying a little bit more expensive one. You see here. Can you see? Let's see. Can you see this guy? It's $60 from Amazon. The power supply died. I don't know why. Probably $10 one couldn't handle the kind of current, total current we need. And I used the PC's switching regulator, turn on. It's got a lot of noise, and I thought the switching regulator is very noisy, and I removed that, and now using this good power supply, there's no noise, but still noise. So now noise seems to come from this guy, and I remove this and use the pulse generator from this oscilloscope. Let's see. let's see. This oscilloscope can generate the power, the pulse, and the pulse is AC, not the DC, so it's skews the waveform quite a lot. But here is a gate. One side is the input of the pulse, and this is outside, and set the current mirror to have all the gate and input to output drivers same current. Okay, so this is kind of still noise coming. So I think noise coming somewhere else, not the I need to identify where the noise is coming. But switching is working. Input and output pretty much same. Waveform is very skewed because input is a negative voltage is amplified by TTL type of inverter, and using that, so it's very skewed. Okay, but it's working. Okay, so that's the end of high speed. Let's see. Even this discrete TTL, how much speed it is. Let's see. This is 1 nanosecond. It's less than 1 nanosecond. I mean 1 microsecond, and it's over the limit of this oscilloscope capability. Probably nanosecond. Okay, that's it.